Okay, welcome to our next session. We're looking at series circuits, and of course we want to consider batteries in series and resistors in series, and maybe we'll also look at capacitors and inductors in series as well, which are some other components. When you're asked to connect a circuit, say you're given this basic circuit here with a battery, this is all we have been considering so far, right? One load, one resistor. If you're told that, hey, we have more than one load, right? How are you going to connect it? There are only two ways that you can connect those loads. Either you're going to connect them in series or you're going to connect them in parallel, right? So if you have another load, what you can choose to do is to just connect this load in this configuration, right? This is how you can connect another load. Or if you're given a circuit with one power source and one load, and you are told that, hey, we have another load to connect to the circuit, then you can choose to connect it in series. And connecting in series would be that you you connect one end of the load or two ends of the loads together, and you connect the others to the battery. So this would be in this is how you connect the load in series, and this is how you would connect it in parallel. Now we have certain things to share about each of them, but for now we're just going to share series. All right, so we are connecting two components in series. You can see here that the one component must be connected to power supply, the other component is connected to the leg of the other one, and then the other one is connected to the negative component of the power supply. Right, so let's start with batteries. Right, so all of us have used batteries before, and of course we know that the voltage across a battery is about 1.5 volt, right? So this is a cell, 1.5 volts, right? Most circuits we have they need or they require a voltage of which is greater than 1.5, and so what we do is that we connect the batteries in series to increase the voltage. So if I had a Game Boy that required 6 volts, then I would use 4 batteries, right? So I'll just draw a circuit here showing the connection of 4 batteries in series to give us that to give us that 6 volts, right? So if we took our voltmeter and we're measuring here, we would get 6 volts here, right? So you can see that when we connect power sources in series, the voltage adds up, right? And we have used this before. Most of your items that you have that use batteries, the batteries are normally connected in series to give approximately, this would give 6 volts. So 1.5 times 4, which would be 6, right? So most battery cells, the voltage is about 1.5 volts. Now, of course, the lithium polymer cells, the voltage for that chemistry is about 3 volts or 3.6 volts. And of course, if you want to have a higher voltage, these are connected in series to give you that higher voltage, right? So, and you will see that when we look at resistors in series, we will see a similar thing happening here, right? Where we will have the voltage drops adding up to form our supply voltage. So let's talk about the current here. In this circuit right here, the current is going to be the same as the current of one cell, right? So whatever current that one cell gave out, if that current was maybe 1.5, let's make it practical. If the current that was coming out of the battery was 1 ampere, right? When you connect the batteries in series, the total current will still be 1 ampere, right? Even though you have 4 cells in series, the total current is still 1 ampere, right? However, if you connected the batteries in parallel, and this is done to supply more current, so when the batteries are connected in parallel, that's all the positive sides are connected together and all the negative sides are connected together, right? Now the voltage across all of the cells is 1.5, right? So again, the voltage across all of these will be the same, 1.5 volts, and then the current coming out of them is now going to be 4 amps, right? You will see that each battery will supply 1 amp. This one will supply 1 amp, and now we have a total of 4 amps available to us if we connected our batteries in this configuration of parallel, right? So this is parallel. This series is just for the circuit above here. So this is connecting the batteries in series. We see that the voltage goes up to 6.5 volts. but the current is still 1 amp. And here the voltage stays at 1.5 volts here for the batteries, whereas the current now, we have 4 amps available because we have the current for each battery. Okay, so this is the resistors in series. Let's talk about this is batteries in series. Let's go to the resistors, right? So we want to see, well, okay, how does the resistor in series affect our circuit that we were using, right? So before we had, let me just give an example. We have a circuit here with one load, correct? And let's use so we have a 10 volt power supply, and say our voltage, our resistance is 10 ohms, right? When we connect resistors in series, there is only one path for the current to flow, and because of that, that current will see all of the resistors that are present, right? And all of these resistors affect the value of the current. So let's say that our R1 is going to be 5 ohms and our R2 is going to be 5 ohms, right? So we are saying that the current that is coming from this battery, and of course the current coming from the positive terminal, is going to see that load right here, and that will determine the this resistance will determine the current based on Ohm's law. So we already know that I is going to be equal to V over R, right? So the R that is being seen is actually this load. Now when we have, if this is the series circuit right here, when we have this load here, we are saying that the current that is coming from the battery is going to see this as a resistance, and it will also see this. So you can ask yourself the question, what is the total resistance that the current is seeing? This total resistance is going to be the sum of all the resistors in the series circuit. Again, there's one path for current to flow, so RT is going to be R1 plus R2 plus R dot dot dot, right? However many resistors there are, all of these are going to be seen by the current, and they will affect the current, right? So our total resistance is going to be a sum of the resistors. So now to calculate the current here in this circuit is going to be the voltage over the total resistance. Now in our case here, this is going to be, let's say we have 10 volts here as well. It's going to be 10 over 5 plus 5, right? So our RT is 5 plus 5. In fact, I can put it right here. RT is equal to 5 volts plus 5 ohms. So this gives us 10 ohms. All right. So again, our current is going to be 10 volts over 10 ohms, which is equal to 1 ampere. Similar over here, it's going to be 10 volts over 10 ohms, which is equal to 1 ampere, right? So the first thing we have established about series circuits is that the total resistance that the power supply sees is the sum of all the resistors, right? The second thing we want to discuss is the current. Okay, to calculate the current for the series circuit, we need to have the voltage over the total resistance of the circuit. So that's the second thing we want to establish for the series circuit. The third thing we want to establish is that we can actually measure the voltage drop across each resistor, and this voltage drop is going to be equal to the battery voltage. So let's come to the series circuit, right? If you take your voltmeter and you measure the crosshair, you took a voltmeter and you say, what's the voltage across this hair? Is going to be equal to 10 volts. That is because the total voltage drop is always equal to the source, right? So if the source is 10 volts, we have one load. It means that we have 10 volts across this load. Now think of it. If you take your meter and you're measuring from hair and hair, you're going to get 10 volts. When you go across the source, you're going to get 0 volts because now you are at the same potential with ground, right? So all of the voltage is dropped across this 10 ohm resistor. Likewise, now in the series circuit, something different happens, right? Since all of the resistance is not in one resistor, but it's in different resistors, we're going to have a voltage drop. We're going to have a voltage drop across each resistor. So VR1 and also VR2, right? This voltage drop, so this is the law we want to establish, that in the series circuit, the same 10 volts is going to be dropped across all of the components. Now we only have 2 resistors, so it's dropped across these 2 resistors. But the important thing to note is that this voltage drops will always add up to our supply. So the law that I want to introduce is called Kirchhoff's voltage law, or KVL, and it says that Vs is equal to VR1 plus VR2 plus whatever other voltages that we have in the circuit, right? So again, these two voltage drops must add up to the source right here. Okay, now this is Kirchhoff voltage law. The second thing we need to figure out, so we talked about the resistance, we talked about the current, now we're talking about the voltage drops. Then the next thing we need to discuss is how can we find this voltage drop? How can you find VR1 and VR2? Now there are two main ways that we can find it that I will share with you. We can use the Ohm's law. So the first way is to use Ohm's law. And the second way, we're going to use the voltage divider equation. All right, so let's start with Ohm's law, right? So again, you saw earlier that we can actually apply Ohm's law across a power supply, and we can also apply Ohm's law across a load. So in this case here, if we know the current that is flowing here, we know the current through the resistor, and we know the resistance of the resistor, we can find the voltage across the resistor. So we can say that VR1 is going to be equal to the current flowing through the resistor, which is the same as I. Okay, there's only one current in the circuit. I times R. So VR1 is the resistance times the current flowing through the resistance. That gives us 1 ampere times 5 ohms, which gives us 5 volts, right? So again, using Ohm's law, we calculated the voltage across this resistor to be 5 volts. Now keep in mind that according to this equation, these two voltage drops need to add up to the source. And so if we found that the first one is 5 volts, then of course we expect the second one to be 5 volts as well. And that does make sense, because if you look at the resistance, they have the same resistance. And because they have the same resistance, they will have the same voltage drop. And this is what the second method tells us, the voltage divider equation. It tells us that the voltage drop is based on the resistance, right? In other words, a fraction of the fraction of the voltage drop is actually the fraction of the resistance. So you will see that the amount of voltage across a resistor is based on the amount of resistance of that resistor. So let's calculate VR2 using the voltage divider method. VR2 is going to be equal to R2 over the total resistance. So the fraction of R2 over the total resistance times the source. And that makes sense because we are saying that the voltage drops add up to the source. So if you have some resistance, it's going to be a fraction of the source, right? In this case here, we're going to have 5 over 10, which is a half, times Vs, right? Or times, so a half times 10 gives us 5 volts as well. And of course, this same method, we can apply Ohm's law to VR1 and also VR2. We can apply the voltage divider method to VR1 and also VR2 as well. So again, this is the important part. So again, for series circuits, we need to know that RT is going to be the sum of the two resistors. We also need to know that the current is going to be the voltage over the total resistance. Then we need to know that Kirchhoff voltage law applies, where the total voltage drops is going to be equal to the voltage source. And then we also need to know that we can find the voltage drop across the resistors by using Ohm's law, where we multiply the current by the resistance. Or we can use the voltage divider method, where we take the fraction of the resistance over the total resistance times the source voltage, and we will also get the voltage drop across the resistor as well. So this is it for series circuits. Again, we look at batteries in series, we look at resistors in series. Of course, as we continue, we will look at other components like capacitors. And of course, the symbol for the capacitor is this, representing the two plates. And these can also be connected in series as well, because they have only 2 legs. Right? We will also look at inductors. All right, this is the symbol for the inductor. And this can also be connected in series as well. All right, now of course with these you don't directly calculate the resistance, but we can discuss the voltage drops and we can discuss the currents as well. Okay. So again, this is Professor Scangrella signing off. See you on the next one. We will talk about parallel, and of course we will try to work some examples as well. So this is just one example. I encourage you to just change, you can add more resistors, you can change the resistance values, you can change the voltage, and you can also get the results as well. So the second part of this video is going to be a simulation of a very similar circuit. So just let's meet you over there.